Okay. Welcome, guys. So in the previous that we already talked about ideal and quotient ring, right? So in this video, let's investigate more. Okay. So yeah. Okay. So what I want to say is that basically people will use ideals to investigate rings. Okay, so the easiest idea, if you are the first time, right? The easiest ideas that you should ask is a number of ideals related to a ring, right? So what you are trying to guess is that people guessing, or I guess, is that the less ideal. So if you have a less ideal, then the ring should be simple, right? Our ring should be simpler. Okay, so this is your intention, right? Because if you have ideal I, then you can make a quotient ring. So intuition should view is that if you don't have some, if you have less ideal, then that means the quotient ring you can build is not too much, right? So it means that the ring should not be complicated. Okay, so here comes the fact that the theorem, which is the first theorem that R is a commutative ring. Yeah, so here from here now that we already always consider commutative ring with the identity. Okay, and the only ideal, if the only ideal of ring is zero in itself. Oh, by the way, this zero is just zero ideal, so there's only one element. Then R is a field. Okay. Okay, so that means this fact that shows what our guessing, right? Because if you have only one ideal, then if the non-trivial ideal is only R itself, then it must become a ring. It must become a field. Okay, so let's prove. Okay, so in order to prove it, remember the ring, the field, right? Field is a division ring, commutative ring, right? Commutative division ring. So non-zero element, I should say, commutative ring with unit, and the non-zero element has inverse. Okay, so all we need to show is that non-zero element has inverse, then we prove it is field. Okay, so the proof is just easy, right? Take a non-zero element in R, and then we take the ideal generated by A, so which is basically the RA, which R belongs to ring. Okay, so your exercise for you is to check that A is ideal. A is an ideal. Okay, so this is trivial. Okay, so you can check by yourself. So now we already know that A is non-zero, right? So that means A cannot be the zero ideal. So A must be a ring, whole ring. Okay, so which tell you that and then one belongs to ring, right? So that means there's a B belongs to ring such that the BA is one. Okay, so B is an inverse. Okay, so that means R is a ring. R is a field. Sorry, R is a field. Okay. Okay, so now we can discuss how to make a ring become a field, becomes a field. Okay, so let's talk about a maximum ideal. So the maximum ideal, this is the first important, which should be the most important ideal. Okay, so that's definition. So definition of the maximum ideal means that whenever, let me just write down word, whenever U is an ideal of R, such that so the maximum ideal is called M, such that U cover it. So U is an ideal greater than M, but less than R, right? Because whole ring is R. If you have any ideal is satisfy this property, then U must be M or U is R. So that means that there's no intermediate, no non-trivial intermediate ideal between the maximum and the whole ring. Okay. Okay. And Yeah. So okay, so this is a theorem that I will not going to prove. So if you start from a ring with commutative ring with unit, then there is a maximum ideal. Okay, so in order to prove it, you need to use an axiom of choice. So let me just sketch. So in order to prove it, right, you need to say that if you have two ideals, if you have a lot of ideals, right, then you can define the partial order, right? If you have two ideals, then you can say, oh, this I1 includes, so this I1 is less than I1 is contained in I2, which means I1 less than I equal to I2. So this is the partial order. Okay, so that means you can, at this ring, right, you can define the sets of the rings, so the set of ideals, you can define a partial order. Okay, so you can ask about a maximum chain, right? So, sorry, if you have a chain, then there's a upper bound, right? The whole ring is the upper bound. So by Zhong's lemma, there's a maximum element here. Okay, so you take a maximum element M, and then you ask whether, and then you prove that M is a maximum ideal. Okay, and then this is trivial. If M is not, then you can find U such that cover it, right? So which U is strictly bigger than M. Yeah, so yeah, basically this is not just a sketch. Basically, I already write down all the details. But yeah, but the idea is that just use a Zhong's lemma and define a part. So this is the same as you try to prove that every vector space has a basis, right? You just use a Zhong's lemma. Okay, but what I want to say is that let me maybe talk some examples. Okay, so let me just talk two examples. So let's say R is an integer, right? So what is the maximum ideal of R? Okay, so you can think by yourself, right? But let me just provide example. Let's say 2. Okay, 2 means 2z, right? So I can admit that 2z is the maximum ideal of R, right? So let's take it. So I try to prove it. Suppose there's another U which is not the same as U as z, right? So that means U must contain an R number, right? Because this is the even number, is a whole integer, right? And the U, let's suppose that 2z is not maximum, so that means there's an ideal U such that U contains R number, right? But you see, if U contains the R number, let's say 1, right? Then you can add 2, it becomes 3, it becomes 5, right? Because any element in R, any element add U, any element in U added the element in R must still be U, right? So R plus U still be U for any R belongs to R, U belongs to U. So now your R is integer, right? So that means if you have 1, then you must have 3, you must have 5, right? You keep going, and finally your U becomes Z. Okay, so which say that 2Z is a maximum ideal. Okay, and then you can show that the prime number, any prime number generated by prime number multiple is a maximum ideal. Okay, and the 4 is not maximum ideal, right? The 4Z, right? Because the 4 can the multiple of 4 can strictly less than multiple of 2. Okay, so now this is so now this 4 is not maximum ideal. It's not maximum ideal. Okay, and also let's talk some algebraic geometry example, which is also somehow like very not very interesting. So let's see, we take our ring to be Zx, right? So Z is a complex field in the polynomial ring, right? And then you can ask what is the maximum ideal? Of a ring, right? So for example, X is a maximum ideal. And the reason you can check by yourself, let's say, suppose U contains X, which is not the same as X, right? And but you also not the same as C, right? So obviously that U is a so in the future we will prove that this is the principal ideal domain. So that means any U just can generate by some variable, generate by some polynomial. Let's say generate by f of x. Okay, but the problem is that yeah, so generate by f of x. Right, but the problem is that since U contains x, right? So f must be, so f of x must be must have a root. Okay, must has a root x to 0, right? Right, but somehow like you can check by yourself that okay, so you might think that your f of x, right, can be chosen to be for example, let's say x let's see yeah, so f of x must has a root at x equals to 0, right? So you might think that yeah, so but the problem is that this is already irreducible polynomial, right? So somehow your f of x, if your f of x try to be x times x minus 1, right? This is not allowed, right? Because you need to contain whole x, right? So your case is that yeah, so if you say that your f of x is generated by x times x minus 1, then it's not allowed, right? So you see so you see in this case it's somehow hard to understand why you should be why x is a maximum ideal. It's not very obvious now. Okay, so we will talk about the theorem that show that why people can see x is a maximum ideal. Yeah, somehow like in this example, I forget how to make an argument that why is this maximum ideal. I mean from the definition. Yeah, there's an interesting example. Okay, maybe we don't. Let's see. Okay, so let's talk about this example. Okay, so this example says that if you see ring to be all the real values continuous function on closed unit intervals, so I should say that f ring is a function defined on interval 0, 1 to real number, which is continuous. Okay, so easy to check this is a ring. Okay, so and then you take m to be all the functions such that half is 0. Okay, so claim m is a maximum ideal. Okay, so somehow this type of so prove something is maximum ideal is not, somehow can be very difficult. Okay, so let's say if you have u, right, you cover m, but not the same as n, right? That means you can find a function g of x such that g of x do not belongs to m, and but it satisfies this property, right? So that means g half g, okay, so so it's not belongs to m, right? So g half cannot be 0, right? So it must be something called alpha. Let's call it alpha, which is, so I should say alpha, which is non-zero. Okay, so that means g half will be alpha, which is non-zero. Okay. Okay, so now let's define h to be g of x minus alpha. Okay, so in this case that h half is just 0, right? So we should tell you that h must belong to m. Right, so h must belong to m. Okay, but the problem is that you know that h must belong to m, right? But m is in u, and the g is in u, right? So who should tell you what? Who should tell you that h minus g is in u, right? So who should tell you that alpha is in u? Okay, but alpha is non-zero, right? So that means alpha inverse is identity in u, right? But if u is ideal, right? Since u is ideal, if 1 in u, that means the whole ring in u. Okay. Okay, so the most important theorem up now we need to prove is that if R is a commutative ring with unit, and the M is a maximal ideal of R, maximal, theorem. Theorem says that R quotient M is a field if and only if R is a M is a maximal ideal. Sorry, so I should say. So if you have an ideal which is a which is an ideal of ring, then R quotient is a field if only if M is a maximal ideal. Okay, so proof. So the proof idea is just using the previous video of the using the correspondence theorem. Okay, so let's see. So remember that let me just write down a quick remind you guys what is the correspondence theorem. Sorry, let me just. Okay, she give me one minute. Okay. Okay, so let me just quickly remind you the correspondence theorem. So if you have a homomorphism from ring to R prime, which is onto ring homomorphism, and then you take the kernel, let's say the kernel phi is let's say S, okay, okay. And then we know that the theorem, the correspondence theorem says that the set of ideals larger than K is 1-to-1. Cover K is 1-to-1 to the ideal of R prime. Okay. And also R prime by the isomorphism theorem is just R modulo K. So the set of ideals greater cover K is 1-to-1 corresponding to the ideal of R prime. And also R prime is isomorphic to R quotient K. Okay, so from here, okay, so I don't have. Let me just add more. Okay, so what we need to what I like to show. Then we need to prove. Then we prove that if only R quotient M is a field, right? This is what I intended to prove. Okay, so in order to prove it by the correspondence theorem, right? That's denoted the map from R to R prime, right? This is R quotient M. Okay, so by the correspondence theorem, the maximum, the ideal greater than M, right? This is kernel, just M is the set of the ideals. So this is a set. It's a set of ideals of R prime. Okay, the problem is that there's no ideal greater than M, except R itself, right? So there's only here called R. Okay, so the set of ideal in R prime, there's only one natural ideal in R prime. So remember the correspondence means that in order to the correspondence means that you use phi to commute, right? So the only ideal which is larger than M there's only two. Let me write down. The only ideal larger than M is M or R itself, right? And then if you use phi to map it, phi of M map to 0, and then phi of R map to R prime, right? So if M is a maximal ideal, if M is a maximal ideal, which tell you that there's only two ideals of R prime. So only 0 and R prime is ideals of R prime. So by previous theorem says that the only ring which contains only two ideals must be field. Right, so R is a field. Okay, so at least means that we prove these directions. Okay, and the same is that if R quotient M is a field, then I can also consider this map, right? And the set of the ideals in R prime is only 0 and ring, right? So because this is a field, so the only ideal is 0 and R prime, right? So if you map it, if you map inverse, then you get phi inverse 0, you get M, and the phi inverse of R prime, you get R, right? So there's no non-trivial ideal cover M. So by definition, M is a maximal ideal. Okay, so the maximum ideal is somehow abstract, right? But by definition, if you want to prove the property, then you only need to use the correspondence theorem. Okay, so this is the final proof. Okay, see you guys next videos. Be sure to subscribe to my channel.